Hi, good morning, everyone. My name is Wenhui, and I'm representing Bytedance, and this is a project collaborating with Ken Lu. Firstly, I will say thank you everyone for attending because it's Labor Day, National Labor Day today, and people are doing labor work for the Labor Day. Thank you so much for your hard work. And the presentation today here is Zero Trust Architecture for AI Workloads. This is a collaboration project between many companies, between the ARM, Intel, AMD, and I listed all the contributors here. So firstly, I would like to give an introduction of overview of how the large language model system looks like and what are the valuable assets in the large language models. Then I will go through the threat model of the how we attack the large language models and what should be protected. And then afterwards, I will go through the architecture to support the security and safety of large language model systems. Then afterwards, I will show open source code available, and in the end, I will show the demo to show how the system works. So this is a representation of a very high-level overview of how the system of large language model systems look like. So firstly, the customer will send queries to app hosting. App hosting will send the request, embedding the request, and send it to the orchestration in the edge cloud. And the edge cloud, through the Llama index, it will send the request to the central cloud where the training of the large language model is. Then the large language model will then request the prompts with a few short examples from the playground. For example, if you are supporting the Copilot program, then your code will serve as the playground document and will be embedded and put into the insert into a Llama index using a representation of a rag. And then together, it will send, afterwards, it will send a request to the APIs and the plugins and query the vector database models, as you see on the very right up corner. And then the vector database will send back to a request to the large language model. And after learning, it will send the result to LLM cache. Within the cache result, and after logging, we'll send the request back to the app hosting and output to answer the request of the prompts that given by the customers. So in this process, we could see that for the queries submitted by the users, the information flow goes from the app hosting to the orchestration and all the way to the vector databases. And also, the information will be left in the LLM cache and logging of the LLM ops as well. So which introduce the privacy concerns of where the customers will probably put their code, private information, PPIs, into the system, and it will be left in the system. So how could they protect the customers from on this side? As from the introduction of the overview of the large language model systems in the previous slide, we figure out okay, there are three parties in this whole system. One is a model vendor, the second one is a prompt feeder, which are the customers, and the third one is a cloud service provider, which provides both the edge cloud and the central cloud, and also supports the services of VectorDB and LLM cache. So for what are the assets of the model vendors they host? They host the foundation models, such as Llama 2, Llama 3, or ChatGPT, or in our company, it's called Seed. And also, when we are supporting a large customer, we have model parameters, which are fine-tuned foundation models, which are hosted by the model vendors. For example, for medical, we have some medical tools, domain fine-tuned foundation models. And for the prompt feeders, what are the assets, valuable assets are there? So the end customers, they have their private information in their prompts. So these are within their territory. And the fine-tuned models belongs to both the model vendors and the prompt feeder. And some of the rag knowledge database, as we talked before, such as the code base in the Copilot or the documents of your company, they build up the rag knowledge databases from there. These the ownership belongs to the prompt feeder. And what are the properties of the cloud service provider? The model serving infra and the secrets behind all the efficient serving and isolated serving for highly utilization of the GPU resources. This kind of the infra code, they belongs to the cloud service provider. And in this system, three of the parties, both the model vendors, prompt feeders, and the cloud service providers, they don't trust each other. So how can we build a system to support the zero trust architecture between the three parties? So before we are proposing the solution here, explaining the solution here, we would like to go through the threats in the systems, which will threaten to either to steal or leak the data or do data poisoning or model theft for the previous three parties. So in model training time, there are lots of threats that might happen to our model vendors, both to the third-party model vendors and inside model vendors. For example, we have training data leak, which is unauthorized access or exposure to the training data. And we have training data poisoning, which deliberate and manipulate the training data to compromise the model's integrity. And we have development model theft, which means maybe our cloud service provider, or maybe we are using GCP to train or GCP or NVIDIA cloud to training the model. This cloud might have unauthorized copying of the AI model during the development. And also, we have the development time model poisoning, which means the cloud service provider might tamper the model itself during its development. Or the end customers, might send out some pointers prompts, which will steal the model from the very end API. For the serving time threats, we have evasion, which is the end customers will fold the model for incorrect predictions or classification. And also we have the model theft, as we just talked about before. We have model inversions, data disclosure, membership inference, denial of service, model service, denial of service from there. And we have lots of prompt injection, which will inject in the fine-tuned model to make it send out the harmful prompts from there. So how could we prevent all these threats from theft, alteration, poisoning of our system and our model, and also the privacy data from our end user? So we propose a zero-trust architecture to protect the AI assets. Firstly, in a very high overview, we believe there is a certificate authorization, as we all know. So the certificate authorization will certify the model vendors, and at the same time, it will sense the hardware, which are the CPUs, or the firmware on top of the alongside with the CPU. And the remote tester, where the customer will have access to, it will request the remote testing server to get verification from the certification authority to say, okay, the model vendors and the CPU hardware, the CSPs, are trusted parties from here. So there are three steps that has been going in this process. One is that the CA signs the hardware. The second is the CA signs the model vendors registration, where the model are served, and the servers. And also the customers will request a verification with the CA through the remote attestation server. And in this process, whole system will provide the verification and validation, which means we will validate all the data entering the system, like a guardrail. And this includes the data used for training AI models and data processed by the AI models. For examples, the inputs, the prompts to the system, and documents sent into the system, and also the output of the models to make sure that models won't return the harmful results. And also, we use end-to-end crypto techniques in the CSP side to verify the integrity or the authentication of both the code and data source. And also, we ensure the least privilege, continuous monitoring, and end-to-end encryption, and regular updates and patch management in the system. So what is this technology called? It's called a trusted execution environment. So the trusted execution environment preserves data confidentiality, which means it does not allow unauthorized entity to view the data while it is within use of the TEE. And the second thing it preserves is data integrity, which means unauthorized entities cannot add, remove, or alter data while it is in use within the TEE. And third one is code integrity, which is unauthorized entities cannot add, remove, or alter code executing in the TEE. So the user scenario of the TEE are like this. For example, our model as a service or vector database applications are running as containers in the system. And during the deployment, we do a testation for all the user space code. And the testation is authorized and authenticated by the hardware. And the hardware is assigned by the CA, where the CA will give the identity and authenticate it from there. So this deployment model has two stages. It ensures at the container launch time, the integrity measurement and the testation. It also ensures at application initialization time, we have the integrity measurement and the testation. So both the model vendors and the customers could get a third-party CA verified and tested boot record and event logs and verify from there. So during a deployment for the trusted execution environment, we found there are lots of challenges. For example, there are lots of deployment models. And the different deployment models have different ABIs and APIs supported by different hardwares. And there are lots of attestation protocols that needs to be unified together to support across the different hardware. And also we are facing I/O bottlenecks, etc., and kernel bypassing problems along the way. But today, I'll be focusing on the first three challenges that brought to attestation and how we counter and how our open source code actually capture this part, help resolve the problem. So the first challenge is we have various deployment modes. We have confidential VM, and maybe some of the customers, they want to run their MES or want to run their databases on the VM directly. And we have confidential VMs with a containerized application deployment model. We also have confidential cluster because sometimes when people we have lots of their requests going on from the end customers that we want to always balancing it out. And we have confidential container. Also, we have confidential functions where the function as a service will run serverlessly, and both model vendors and the cloud service vendors, the cloud service providers will provide awareness hardware solutions for the model vendors and end customers from there. And for all these various deployment models, we want to support the auto scale up, the snapshot, and HPA for the workload. And also, we want to support automatic scale out in large scale under the TEE field. And the second challenge is there are different hardwares, and these hardware vendors actually have exactly different hardware interfaces to the testers. For example, the Intel TDX supports attestation for applications through the RTIMR registers in their firmware. Additionally, the Intel provides IMA backend to RTIMR. However, these are the two non-upstream versions of patches. On the other hand, the AMD hardwares, the SEV-SMP, they support application attestation through the VTPM and other means. And we also have various APIs to support the different user space level dependent attestation. And for example, the interface solutions provided by the Intel and the AMD differ. The Intel TDX supports application attestation through the IMA interface, which is the integrity measurement interface in the Linux security module. Whereas the AMD SEV-SMP supports it through the HMAC update interface. And ARM supports it through the RSI interfaces. Furthermore, the users need to manually analyze the application dependencies, create attestation policies, and integrate them into the authentication process through the specific interfaces. And third challenge is that currently, our different hardwares are supporting various attestation protocols. For example, on the transplantation layer, we have TLS, and it also has SPDM. And for the remote attestation protocols, for the Intel ones, the SGX supports DCAP and EPID, and TDX supports DCAP. And ARM, on the other hand, it follows the PARA protocol. So our solution here is we, together with Intel, AMD, and ARM, we build a unified API for confidential computing, which means we have unified southbound API evidence, application binary interface, for the event logs to access across the different TE hardwares. And then on the northbound API, we have end-to-end measurement across the different frameworks. So for the unified southbound API, which we access the event logs and such as for the evidence across the different TEs. We support the config TSM, and also we support the TCD event logs through the ACPI CCEL table. For the AMD ones, they use the VTPM interface. So our software also supports the DevTPM0, which are where the PCRs and code are exposed through these device interfaces to the user space. And also, we support the ACPI TPM2, where the TCG event logs will transport it from the hardware TPM to here. And on the other side, we support in our trusted API, we support integrated measurement register, TCG event logs, and code. And this code will be sent to the remote attestation server, where the customers will be trusted. This remote attestation server will be signed by the CA, and the customer will trust it from there. And for the northbound API, we support not only confidential VM, but also we support confidential cluster. And currently, we are working on the confidential container, where the containers are running inside of the confidential VM. So this is the overview of the CC API project. we have the interfaces, like these are the components of like a CC API project. We support like a CC performance profiling and CC operators. So in CC performance and profiling part, we have integrated and read the logs from CCEL and RTMR and the VTPM and send it to the IMA in the Linux kernel. And IMA will send the stuff and attest the device plugin, daemon set, and sidecar from there. And for the interfaces, we support confidential computing measurement, attestation, event log, and quote APIs. So like both the IaaS, PaaS, and SaaS, they don't have to worry about the differences between the different frameworks and deployments, and they could use our CC API software directly, no matter what deployment you want to provide to the end customers. And for the APIs, if you want to use it, we have exposed get default algorithms, which will return a TCG algorithm registry object which tells the default algorithms. And we support the get measurement count, which returns an integer telling the count of measurement registers. And we support get CC measurement, which get measurement register according to the given selected index and algorithms. And we have the get CC report, which will get a code for given nonce and data. And a nonce is generated by remote tester and hardware, and which the generator is assigned by the CA. And we have get CC event log, which supports get event log for given index and count. We have replay the CC event log, where the customer, if they don't want to use the Intel ITA service, or if they don't want to use like our CSP service, and they want to test on their on-premise or even on their local computer, they could download the event logs and download the report and replay the CC event log on their local computer to attest the whole process. So the current status is like depends on the different customers. Some of them, if they want to like use Python to write their own attestation server, we support Python, Go, Rust, VM SDK, and container SDK on both. So if you are supporting the confidential VM, you could use the VM SDK. And if you are supporting the confidential cluster or confidential container, you could use the container SDK. Depending on which language you prefer, you could always integrate from there. And we have supported the TDX module attestation, the firmware attestation, and the firmware will test the IMA will test the container, which means we support the whole node and container measurement at this time for the code. And here is how an example of how the node and container measurement looks like. And on the left is a detailed explanation of the event logs. We'll show the total number of event logs. The first event log always has the specification ID event complaint to the TCG standard. And also, we show which integrity measurement register index it is, where previously in here, it is equals to some registers in the PCR as well. And we'll also show the digesting for raw event data, list of random algorithm ID, and digest value complaint to the TPM hazard, standard. And we also, in the event log in entry, we follow the canonical event log standard. And the canonical event log standard, we print out the encoding type, record number, and the content type. And also, we support the digesting info and detail the content from there. So here is a demo.
Hello, this is a preview video of CCNP container management. In this video, I will introduce how to use container management in the Kubernetes environment and the Docker container. Here is a TDX with Kubernetes installed. We can see all the pods. Yeah, from here we can see the Kubernetes component has been deployed, and we also deployed Kubernetes a node feature discovery deployment to discover the TDX guest feature, and we also deployed a CCNP server as a demo set and example pod named CCNP management example. Yeah, we can go into this pod by execute this command. Yeah, we have put a Python script in this pod named CCNP management. Then we can run this script. Here are some information about this script, such as get the CC report, get the CC event log, and get the CC management, and verify the event log. First of all, let's see the event log here. Yeah, lots of event log has been recorded for this pod. In the beginning, we can see the start from the TDX boot hub. The OVMF had recorded some event log such as the platform firmware, the verbal driver configurations, and some other information recorded by the OVMF. And at the end of the OVMF event logs, we can see some event log has been appended to the event log list, such as the container D, process name and its parameters, and the kubelet processes and its parameters, and the container D shim run C and its parameters. This was configured by a policy file here for the CCNP server. Yeah, in this policy file, we can see the backend is IMA, and the algorithm is SHA-384, and the CCNP server will measure the system processors and its with its parameters, the Kubernetes configuration and its pods, and we also set the container isolated to true. That means the container cannot access the other system information or system event log, system measurement, and it can only access the process executed by itself. Yeah. So let's go back to the event log. We can see some process has been recorded with its parameters, and some config file of the container has been recorded, and some executable files has been recorded, and some libraries used by those executable files. Yeah, here is the example of the event log. So the event log can be used to verify the environment, and this this event log also include a hash digest of all the event logs and all the files. Yeah. We can also use this script to get the measurement of the pod, like the IMR. IMR means the integrated measurement register defined in the CC Trusted API, and In this example, we can see we have three IMA index 0, 1, 3, because the 2 was used for the system measurement, like all the system process will be recorded in IMA index 2. So, and all the event log we cannot we set the policy to the container isolated, so the container cannot access this IMAR index and all the other system processes and other containers measurement. Yeah. We can also use verify command to verify the event log by the IMR.
For this verify function, you could either use the Intel ITA service or use the cloud service providers, a remote attestation service service, or the customers could actually download other software and test on their own computer.
Yeah, here we can see the replayed IMR value and we read the real IMR value. Yeah. If they are same, the verification is successfully by the event log was verified by the IMR. Yeah. And the IMR will be used to will be recorded in the TD report. Here is an example to get the CC report. In the report, we are in the TDX environment, so it's a TDX court. In this court, the IMR will be included in the TD report and will be signed by SGX enclave. So the event log can be used to verify the system environment, and the event log can be replayed and verified by the IMR, and the IMR will be signed by the SGX enclave. So we can get the codes and to do the attestation by the third party. Yeah, that's all about the Kubernetes environment example. Yeah, we can also see a Docker example here. Yeah, we have studied a Docker container, and we can go into this container by execute. Yeah. In this directory, I also put the same example Python script named ccmp example. CCMP measurement here. Yeah, we can execute just like we did in the Kubernetes pod. Get the event log. Yeah, we can see all the executable process has been executed in this container, and we also can see most of them is the Python because we just running the Python script, and we also can see some boot event log recorded by the OVMF. Yeah, just like in the Kubernetes report. Yeah. So here is an example of in the TDX to get the event log, and we can also get the measurement here. Yeah. We can verify the event log. Yeah. Here is all the example of how to get the container measurement by the CCNP API. The API is very simple, just like VM SDK of the CC Trusted API. You can see just to from CCNP import the CCNP SDK and use the CCNP SDK instance to get the report, get the event log, and
sorry that we are a little over time. So if you have any questions, we could go over the code offline, and everything is open source. In the PPT slides, we have a hyperlink to the code. Yeah, thank you.